Hey guys, a couple folks asked for a quick tutorial on Le Chatelier's principle and how stresses on systems at equilibrium change the system. So here, a system at equilibrium has reactants combined and form products at the same rate that those products turn back into reactants. So remember that this is all about collision frequency, right? So in the example of A plus B forms C plus D, and C plus D turns back into A and B are colliding successfully at the exact same rate that C and D are combining successfully. So because they both have those successful collisions, recall as successful collisions is they have to strike each other with sufficient energy and orientation. The rates in the forward and reverse reaction are the same. But when we stress a system, they're no longer the same. And the system will shift in whichever direction is favored by that stress until equilibrium is reestablished. The first way you can stress a system is by changing the concentration. So in our sample equation, if we increase the amount of A bumps into B more often. If A bumps into B more often, that means the forward reaction happens more often. The system begins to accelerate in the forward direction, making more products. Now these products, the C and D collisions, actually decrease because the C and D bump into each other less often because all these A's we added, they get in the way. That's called feedback inhibition. So the reverse reaction slows down. So if the forward speeds up and the reverse slows down, there's a net shift away from the substrate we added, substrate A. It shifts to the right to make more C and D and consume the A's that you added to the system. Eventually the rates will be equal again and you're right back at equilibrium. If we're going to talk changes in volume, there's a bit of background we need. So here we've got the ideal gas law. So if you recall, solids are densely packed particles in a lattice. Big particles take up a lot of space, small particles take up a little space, so how many particles you can fit in a volume of a solid depends on the size of the particle. Their volume doesn't really change, because once you compress a solid, it's very difficult to change its volume. The same is true of liquids. So the distance between liquid particles is relatively small, even though they flow and move around. You can't really compress a liquid. You can't really expand a liquid. Pretty much got a constant volume at certain conditions. However, gases, the distance between the particles is so great, kind of like the distance between you and I right now compared to our size. How big I am doesn't really affect how often we bump into each other. The distance is too great. So the size of the particles doesn't really matter in the gaseous state. All particles are so small compared to the distance between them that we say they have essentially the same volume. You can almost assume that they have zero volume compared to the distance between the particles. If you're really attractive or not really attractive, it doesn't matter because there aren't any particles around for you to be attracted to. So it doesn't really matter how attractive you are. As a gas, you all have roughly the same relative attraction to other particles, which is zero. So when we think of an ideal gas, we make these two assumptions. Gaseous particles have roughly the same volume, and gaseous particles all have roughly the same relative attractiveness. Negligible. So if you increase the pressure, you're squeezing the system to a smaller volume. So this means that if you up the pressure, the volume is getting smaller. The opposite is true. If you decrease the pressure, you put it in a vacuum, you're expanding the volume. The system will respond to an increase in pressure by shifting to whichever side has the least amount of volume, i.e. fewest moles of gas. If you decrease the pressure, or increase the volume, it shifts to the side that takes up all that new space, the side that would have maybe the most moles of gas. Changing temperature. So recall that temperature is the amount of kinetic energy that a system has, how fast all the particles are flying around bumping into each other. So remember, for a successful collision, they have to bump into each other with sufficient energy and orientation. Temperature is how much energy is available. More energy means more successful collisions. A reaction happens faster. So if you want to cook your meal faster, you crank up the heat. More collisions means your food cooks and probably burns faster. So recall, each direction in our reaction has energy requirements, forward and reverse, but one of them has greater requirements than the other. That side is more sensitive to temperature changes. So whichever side of our equation has greater energy requirements, If we add temperature, we get more of those reactions. And if we take temperature away, it means we get less of those reactions. If we're going to sketch out some thermochemical equations, we have to understand that an exothermic involves the release of heat. Heat is a product, so it's on the product side of our equation, and the delta H will always have a negative value. So the change in energy, there is a net loss of energy in the system, and it's released to the environment. You feel heat. An endothermic reaction involves the consumption of heat. So energy that's available in the system is consumed. The delta H will be a positive value. So endothermic reactions often result in a decrease in the overall temperature of the system. Energy in the environment is absorbed during the reaction. So when we predict a shift, really if heat is added, system shifts away from whichever side requires the most heat. If heat is removed, shifts towards the side that requires the most heat. Very similar to concentration here. So if you add a substrate, it always shifts away from that substrate. If you remove a substrate, it always shifts towards. Heat, we can treat just like any other substrate. I did a couple examples here that maybe we'll walk through. So here we've got the complete combustion of methanol to form water and CO2 at a constant pressure produces 726.7 kilojoules of heat per mole of methanol. So we've got to write the balanced equation and predict how an increase in temperature would impact this system. So let's look at example number 1. So here we've got methanol, CH3OH, it's a liquid, combining with O2, a gas. We're going to make this an equilibrium reaction to produce H2O, gas, and CO2, a gas. Now, we were told that heat was released. That's an exothermic reaction. So delta H is negative 726.7 kilojoules. There you go. A thermochemical equation, we would include the heat in the equation. So here we've got our methanol, our oxygen, our water, and our carbon dioxide, and our heat. Ta-da! So we include the delta H value, that change in heat, we plug it right into the system. So this would be an example of writing a thermochemical equation. All it has to include is the change in heat, the net change in heat. So the forward requires energy, the reverse requires energy, but the reverse requires a ton more energy than the forward does. So the net difference is 726.7 kilojoules. So how would effective increase in the temperature affect this system? Well, the forward reaction doesn't have much energy requirements, but the reverse reaction has huge energy requirements. So if we were to increase the temperature, the reverse reaction would get much stronger, because this is the reaction that requires heat. So adding temperature drives the system towards our reactants. There we go. Let's do one more example here. Let's do example number 2. So in this case, the decomposition, I can note up here, we did an exothermic reaction where heat was a product and our delta H had a negative value, so this can kind of clue us in a little bit there. The decomposition reaction of ammonia to form nitrogen and hydrogen at a constant pressure requires 46.19 kilojoules of heat per mole of ammonia. We had to write the balanced equation and predict how a decrease in temperature would affect the system. So we're told that ammonia will decompose into nitrogen and hydrogen. And our delta H, because it's being required, energy is required, is a positive 46.19 kilojoules. So if we write out our thermochemical equation, we include the energy right in the equation as a substrate. So because this is endothermic, our heat energy is included right there as a reactant. Now, if we were to decrease the heat available, the forward rate would slow down. The forward rate requires heat to move forward, and if we give less temperature, if there's less temperature available, this reaction happens less often. So this reaction gets smaller, but the reverse reaction is less affected. So the net result here is that the system shifts towards our reactants. When heat was a product, increasing the heat drove the system away. In an endothermic reaction here, decreasing the heat shifted the system towards. And that's thermochemical equations.